Morning everyone. Today we're going to talk about lesson 2.5, scatter plots and line of fit. Your homework assignment, page 96, 3 through 6. So not a very big homework assignment, but these problems do have multiple steps, so it'll be a little lengthy. So data with two variables, such as a year and number of visitors, are called bivariate data. So, if you're talking about like a national park, each year there's some number of visitors. That's what we're talking about, bivariate data. Okay, two variables. A set of bivariate data graphed as ordered pairs in a coordinate plane is called a scatter plot, and so that's what we're going to be looking at. And we even can see here our couple of graphs here. All three of these are scatter plots. Okay, also called a dot plot. We use scatter plot more frequently. Okay. A scatter plot can show whether there is a positive, negative, or no correlation between two variables. Okay, correlations are usually described as strong or weak. In a strong correlation, the points of the scatter plot are closer to the graph of a line than the points representing a weak correlation. So let's talk a little more about correlation and the types of correlation. Okay, so this scatter plot here, this first one, has what we call positive correlation. Okay, positive correlation, the line of fit, you can see the line of fit here would have a positive slope. Okay, this is what we would consider strong. Notice most of the points in the scatter plot are really pretty close to the line. Okay, when we look at our second example of negative correlation, okay, so it's negative because again it has a negative slope. This is a little weaker of correlation because the points are somewhat further than they were in the positive example. Okay, and then lastly we have a graph that has no correlation. This is where the variables just really don't have any sort of relationship going on. Okay, at least not linear. Alright, when you find a line that closely approximates a set of data, okay, you are finding what we call the line of fit. And we're going to draw a line of fit and come up with an equation for that on the back here. Okay, the equation for such a line is called a prediction equation because it can be used to predict one of the variables given the other. Okay, so to find a line of fit and prediction equation for a set of data, what we're going to do, select 2 points that appear to represent the data well. Okay, I'll talk a little more about that when we have an example on the back here. This is a matter of personal judgment. Okay, so it's not going to always be the same for every person in class. You guys might pick a couple different points. Okay, but the line and prediction equation may differ, but they should be similar. Okay, if it's a positive correlation, we should see positive slopes and things like that. Okay, so here the table shows the percent of U.S. households with internet access. So this is the year and then the percent that have internet access. So we're talking years since 95 is our x-axis. So let's plot these points. So 1997, that's 2 years from 95, and there's 18%, which is just slightly lower than 20. So we do our best to plot that point. 2000, that would be 5 years since 95, and 41%, so right above 40%. 01, that would be 6 years, and 50% have that. 03, 54%, so that's 8 years, and slightly above the 50% mark there. And 07, so 12 years, we're at 61%. Okay, so when we draw our line of fit, let me go ahead and get out the ruler. Okay, and kind of talk about this. I would put the ruler up on the board in class, but obviously this is a DLD. So if we look at a ruler, let's put this in here, and you guys are gonna have to bear with me a little bit here. I kind of forget how to move this thing how I'd like. Okay, there we go. So if we've got a ruler going through this, and we kind of just want to connect some points. Let me shrink. Okay, if we maybe start with this point and we're going up here to that point, okay, that line of fit through those 2 points, okay, it's got 2 points above it and they're not very close, so that just, it's not a very good line of fit. Okay, so maybe if we use that first point down at the bottom in this one, okay, well now there's 2 points above it, 2 points on the line, and then 1 point below it. So that's a lot better line of fit. So I would suggest using these 2 points that our ruler is going through here. Okay, and so let's write the ordered pairs of those points. Again, the 2 points I'm talking about here were this first point we plotted and then this point. So if we use that line, again we've got 2 points above it and 1 below it, and that's a pretty good line of fit. Those ordered pairs, that was so that was 2. It was 97 was the year, but that's a year since 95. So 2 and then 18, and the other point would have been, well, that's our 03 point. So that's 8 years since 95. So 8 and 54.7 is the ordered pairs. Okay. So there's our. We've made the scatter plot and line of fit. We've drawn that, and then we've described the correlation. I guess we kind of skipped out on that part, but clearly this line has a positive slope, so this would be positive correlation. Okay. So use 2 ordered pairs to write a prediction equation. So guys, all this is telling me, use the 2 ordered pairs I used in my line to write a linear equation. So what do I need to write a linear equation? I need slope. Again, difference in y values, so 54.7 minus 18 over the difference in x values, 8 minus 2. And so I'll need a calculator here. 54.7 minus 18. $36.7 divided by 8 minus 2 is 6. So I get a slope of 6.11, and then it's 6 repeating. So let's just call this slope 6.1. Let's round it 2 decimal places. 6.12 is my slope. All right. And now, if I've got a slope and I have 2 points, I just need to pick 1 point. Let's call it x1, y1. And I need to use my slope and use point slope form. So y minus y1, 18, equals my slope times x minus x1. And if I solve this, then I have a prediction equation. If I solve this for y, so I need to distribute y minus 18 equals 6.12x minus 12.24. I believe that is 6.12 times 2. 12.24, yeah. Add 18 to both sides to get y by itself, and I have y equals what? 6.12 x plus 5.76. Negative 12.24 plus 18 is 5.76. So that is my prediction equation. Okay, that's the equation of the line of fit, my prediction equation. And then it wants us to predict the number of households with internet access in 2020. So 2020, how many years is that since 95? That's 25 years. So this is telling me if x equals 25, find y the percent. Okay, so I just need to use my prediction equation and substitute 25 for x. Okay, so 6.12 times 25 plus 5.76, and y would be equal to 158.76. And so now this is an interesting conversation to have. When we interpret this result here, this is telling me that in the year 2020, 158% of households are going to have internet. Does that make sense in the context of the problem? Well, certainly 100% would be the maximum percentage of households you could have. So it is kind of interesting. Sometimes these lines of fit don't always make something that It makes logical sense, but of course maybe with population growth and things like that, since 95, the number of households could increase in that manner. Okay, so certainly interesting. Again, you've got three problems. They're all very similar to this, where you've got to plot points, say if there's a correlation, make your line of fit, your prediction equation, and then make some sort of prediction based off of the information given. So, all right, you guys have a wonderful weekend. Thanks for watching this morning.